Once we have a feasible region, that is a region that is bounded by our various constraints, we need to figure out what is the best solution within that region. Because if we can make if we could make anywhere from 10 of this type of pot and 12 or 12 of the other type of pot and 0 of the first, or we can make 0 of either of them, we need to figure out some way of determining what's best here. And so the corner point theorem says that when we have a region, kind of like you can see we have a couple of example regions down here, region 1 and region 2. When we have a region like this, and you're looking for an optimal point, that is either a minimum or a maximum, if that optimal point exists, then it has to occur at one of the corner points of the region. So what I mean by the corner points are, well, for region 1, you can have 1, 2, 3, 4, 5 corner points. These are pretty much exactly what you expect. They're the corners. For region 2, our corner points are 1, 2, 3, 4. There are 4 corner points here. You'll notice the origin is not a corner point here because it's not adjacent to the feasible region. We've essentially shaded over here, and there's only 4 corner points on this particular region. Alright, so if there is an optimal solution, an optimal point, it has to occur at one of the corner points. So what we do, if we're testing to see if this is, if we're looking for an optimal value, then what we can do is we can just test to see what the values are at all the corner points. So if our objective function, that is the thing we're trying to minimize or maximize, looks like this, 6x plus 5y, then I can just test that at each of these 5 corner points. So first off, 0, 0. Let's do 6x plus 5y. That would give us 0 plus 0, which is 0. Alright, well that's kind of boring. At the point 8, 0, we get, what, 48 plus 0, which is equal to 48. At the point 7, 3, we would get 42 plus 15, which is, what, 57. At the point 4, 8, we get rather 24. That's 6 times 4 plus 5 times 8, which is 40. That's 64. And at the point 0, 12, we get 6 times 0, which is 0, 5 times 12, which is 60. So the maximum we get there is 60. Or not the max, but that is the value we get there. Alright, so we've seen that at these 4 corner points, we got values of 0, 48, 57, 64, and 60. It turns out, of all the different possible values that you could achieve somewhere within this feasible region for this objective function, this is the highest one that you can achieve. This is our max. And this would be the lowest one that you could achieve. This would be our minimum, because these are the values we got here. So the question was to find the maximum and the minimum values for z for each of these feasible regions. So you can see we did that here. Alright, so let's look at this other feasible region, this one down here. Or the same feasible region, rather, but a different objective function. Well, if we're doing this, it would be basically the exact same thing, 4x minus 3y. We'll check 0, 0, 8, 0, 7, 3, 4, 8, and 0, 12. Those are the 5 points that I'll check. First we get 0 minus 0 is 0. We get 32 minus 0, which is 32. 28 minus 9, which is, what, 19. 16 minus 24, which is negative 8. And 0 minus 36, which is negative 36. So our minimum right here is the negative 36. That's the largest negative number. And it looks like this one is our maximum. Alright, so that's our minimum. So we achieved a maximum result, rather, at the point 8, 0. A maximum result there was 32. We achieved the minimum result at the point 0, 12. with an objective with a z value of -36. Now, what's going on here? The reason this works is if you think about this this value of z, then you can draw essentially lines of the same values of z. If you said 6x plus 5y equals 0, it would look something like this. Oops, except it should go through the origin. It would have a slope that's close to -1. If you did 6x plus 5y equals, I don't know, 10, it might look something like that. Once we get up to 6x plus 5y equals 64, we're up here. We'll just barely touch that point right there. I know that because this is where we got the maximum result here. And so what you can kind of visualize here is that as you're increasing that value, 6x plus 5y equals 0 all the way up to 10, as you're increasing that, you're just kind of moving this line. You're keeping the slope the same, but you're moving it up this way. And the farther you can move it this way, the larger the value of z you get. And it's when you leave the feasible region, that's when you achieve your minimum and your maximum values. So minimum when you're going this direction, and your maximum when you're going that direction. And you can see that's what this says. You got your minimum over here at the point 0, 0. You got your maximum at the point 48. What happened on this one is our region looks something like this. It's kind of sloppy, but hopefully you get the idea. The region looks something like that. If you were to figure out what's going on here, you'd see that the slope is actually closer to +1. And so if you go in this direction versus in this direction, our minimum and our maximums are going to occur at these points. So we got the point 0, 12. This was actually our minimum. And our maximum was over here. But again, it's as we're moving that line along, it's when we exit the region that we've essentially gone as far in the negative direction as we can here, or as far in the positive direction as we can there, and that's why we end up achieving that minimum or maximum value at a corner point. Now, if we are dealing with a bounded region, so this is an example of a bounded region. Technically, the definition of a bounded region is one that we can draw a circle around, and we contain the entire thing. So it's essentially no, you can bind it within a circle. That's what a bounded region is. If you have an unbounded region, then you don't have this same guarantee. So if you imagine these horizontal or these lines being drawn on here, let's say values are going up as you're going in this direction. Well, you're never going to exit that feasible region. You could always get bigger and bigger. There would be no minimum, or no maximum rather. And similarly, for a line like this, there would be no minimum, because if you're going in this direction, you're going more negative. But this region just continues on forever in this direction, so I could get smaller and smaller and smaller and smaller. So there would be no, there's not a guarantee that you end up with a minimum or a maximum value when you're dealing with an unbounded region. So one thing you can do in cases like this to figure out if you have a minimum or a maximum, something I like to do is to just go a little bit further. So I'm going to test some points that are not corner points. This one up here, if I just go up a little bit from the point 0.8, let's call that 0.9. Or if I go a little bit more to the right from the point 12.0, let's call that 13.0. Now these are not corner points. Whatever we find at these is not going to be a minimum or a maximum. But what it'll tell me is that it'll tell me if the values continue getting bigger past my last corner point, or continue getting smaller past my last corner point. So if we end up seeing a minimum or a maximum at these points, then we would conclude that there is no minimum or maximum. So let's just do the same thing here. Let's go, first off, I'll go 0.8, 3, 4, 13 halves, 2, and 12, 0. And then I'll test my two non-corner points, 0.9 and 13.0. I'm testing those kind of separate just to remind myself that if my biggest or smallest values occur down here, these were not corner points. Alright, and then my objective function was 6x plus 5y. So for the first one, I get 0 plus 40, which is 40. Then I get, 18 plus 20, which is 28. 38 rather. 13 halves times 6, that's the same as 13 times 3 when I cancel a factor of 2, so that's 39, plus 10, which is 49, and 12 0, I get 12 times 6 is 72, plus 0 equals 72. Alright, testing my two non-corner points, I get 0 plus 45, which is 45, and this was, oh, that's 13 0, that's what that says. 13 0, that would be what, 78 plus 0, which is 78. So this is my this is my largest right here. But this is not going to result in a maximum for my feasible region. Because, so you can see it's 78 here. We again have kind of a negative slope, so we're going to end up in a situation like this. We have a value of 78 here. If we go a little bit further, or we have a value of 72 there. If we go a little bit further, we have a value of 78. If we go a little bit further than that, we'd have a value of, what, 84. So we can just keep going in this direction, and we could get bigger and bigger numbers. But it looks like this is the smallest value that we encountered, this 38. This would be our minimum. So this feasible region does have a minimum value. This is at the 0.34, and this kind of agrees with those slopes that I drew over there. You can see if we're drawing these slopes along here, while we're going in this direction, we would get smaller, and we eventually would exit the region here. And we would exit it last when we go through the 0.34. At least that's what this, that's the conclusion I come to here. Now, thinking about whether or not I'm going to have a minimum or a maximum on this one, I already predict that I would not have a minimum or a maximum, because what's going on here is we have a positive slope. This is 4x minus 3y. I predict that you're going to be able to keep going in that direction to get bigger or smaller, and you'd be able to keep going in the other direction to get the other, bigger or smaller, depending on which one. If this was getting bigger in this direction, then it would be getting smaller in that direction. So my prediction here is that we don't have a minimum or a maximum, but let's just go ahead and do the arithmetic to figure that out. 0, 8, 3, 4, 13 halves, 2, 12, 0, then the last 2 points that are not corner points that I just test, 0, 9, and 13, 0. And the objective function we're testing here is 4x minus 3y. So plugging stuff in, we get 0 minus 24. We'll get 12 minus 12. This is negative 24. This is 0. 26 minus 6, which is 20. Then we get 48 minus 0, which is 48. And the last two non-corner points, we get 0 minus 27, which is negative 27. And we get 52 minus 0, which is 52. So this is our smallest, and this is our largest. And you can see neither the smallest value nor the largest value occur on a corner point. And this means that there's no minimum, no min, no max. And I guess I probably should have finished this one up by saying this is the minimum, but there is no max. So just to, really quickly, the corner point theorem says that when we have a region, if there is a minimum or a maximum to our objective function, it has to occur at a corner point. With a bounded region like this one, we're guaranteed to have both a minimum and a maximum. If we have an unbounded region like this one, we're not guaranteed to have a minimum, nor are we guaranteed to have a maximum. But oftentimes we tend to have one or the other.